This section covers the air system features and air flow through a turbocharged after-cooled engine. Click on the section that you want to learn about. In this section, we will look at various features of the ISB engine air system. Click on the section that you want to learn about. The ISB engine uses either the single-piece exhaust manifold or the two-piece exhaust manifold. The two-piece exhaust manifold is used for horsepower ratings of 250 or more for reduction in warpage and cracking due to heat and thermal expansion rates. Both exhaust manifolds contain round exhaust ports unique to the ISB engine. The exhaust manifold is mounted with separate loose towers. This mounting arrangement helps to reduce the thermal stress on the exhaust manifold mounting cap screws, reduces warpage of the exhaust manifold, and decreases the number of exhaust gas leaks at the cylinder head exhaust manifold connection. The ISB engines utilize QE296 and 338 air compressors. These new compressors are more efficient than the previous compressor models. The ISB engine uses an HX35 waste-gated turbocharger matched to the needs of the engine to improve engine performance. On charge air-cooled engines, the intake air is drawn through the air cleaner into the compressor side of the turbocharger. After leaving the turbocharger, the hot intake air flows to the charge air cooler by means of a large pipe. Once inside the charge air cooler, heat from the intake air is transferred to the outside air flowing around the fins of the cooler, thus decreasing the temperature of the intake air. The cooler intake air leaves the charge air cooler and enters another large pipe, which allows the air to freely flow into the intake manifold. A solenoid-operated integral grid heater is installed in the intake airflow to heat the intake air for cold start assistance. The ECM controls the grid heater, turning it on to heat the intake air during cold start conditions. Airflow continues through the inlet ports, creating a swirl pattern into the combustion chambers. After combustion, the exhaust gases flow from the combustion chambers to the opposite side of the cylinder head. Exhaust gases then flow through the single or two-piece pulse exhaust manifold design. The exhaust gas then flows through the divided entry turbine housing of the turbocharger to drive the turbine wheel and pull intake air into the turbocharger compressor. On automotive engines, a waste-gated turbocharger is used for better low engine speed performance and better control of high engine speed boost. The term wastegate comes from the fact that with this style of turbocharger, some of the exhaust gas is gated around the turbocharger turbine wheel and the exhaust energy is wasted. That is, the exhaust energy is not used by the turbocharger compressor wheel to pump intake air into the engine. The wastegate is a normally closed valve in the turbocharger that allows a controlled amount of exhaust gas to bypass the turbine wheel. By opening or closing, this wastegate valve varies the turbocharger boost or intake air pressure within a desired range. Turbocharger boost is proportional to engine speed at wide-open throttle, as you can see from this chart. If we wish to raise airflow at torque peak power, we could use a higher capacity turbocharger. However, this turbocharger results in more boost than we need and excessive cylinder pressures and temperatures at rated speed. Using a turbocharger that produces the additional desired boost at torque peak speed and trims off boost or wastegates the exhaust gases from torque peak to rated speed obtains the desired boost for the entire engine operating range. The goal of a wastegated turbocharger is to keep rated speed power constant, but provide the additional boost needed at torque peak. A wastegate actuator mounted on the HX35 turbocharger controls the position of the wastegate valve depending on the boost pressure it receives from the turbocharger compressor housing. The actuator is a canister with a rod. One end of the rod is attached to a bellows inside the canister, and the other end is attached to the wastegate valve. An internal spring in the canister applies force to close the valve. Turbocharger boost pressure applies pressure to one side of the bellows and tries to open the valve. This force is opposed by the internal spring in the canister. The wastegate valve position is determined by the balance of the boost pressure force opposed by the spring force. When turbocharger boost pressure on the bellows is greater than the opposing spring pressure, the wastegate opens to let exhaust gas bypass the turbocharger turbine wheel. When boost pressure decreases, the spring closes the valve.